Hello everyone. Due to the COVID-19 pandemic, we present our paper remotely. This paper is entitled Hardware Software Co-Design for Dates Classification on Xilinx Zynq System on Chip. I'm Lazhar Khriji with my colleague Dr. Ahmed Chiheb Ammari and Dr. Medhat Awadalla. We are from College of Engineering, Sultan Qaboos University, Oman. The outline of our presentation is as follows. We start by problem statement and objectives, then a flowchart of the proposed system, then the characterization of the classification performance, then embedded system prototyping and performance evaluation, and then conclusions at the end. In problem statement, we can say that Oman is one of the countries that depends on dates as a source of income. It's among the 10 top dates producer countries with annual production of about 260,000 tons in 2017, and every year around this amount. It has more than 250 varieties of dates. These varieties can be distinguished based on their color, shapes, and size. In date factories, we found that the received varieties, of course after harvesting, are merged due to many reasons. So they need to classify them again, and this process has many drawbacks, such as the workers, large number of workers are needed, and consistently less efficiency and costly, which is expensive. Automating classification of dates into different classes using a dedicated embedded computer vision system can help classify the multiple varieties of dates to be fast, accurate, and cheap. However, automating the classification tasks is by itself complex and challenging because of the irregular sample features within the same type of classes, the similarities that can be found between samples from different classes. Then, in our paper, we tried to develop a dedicated computer vision system for automatic dates classification to characterize and evaluate 3 different classifiers and select the best performance. Among them, we say that artificial neural network was used, support vector machine, and K nearest neighbor. Investigate the effect of color, shape, size, and texture features and classification performance. Investigate the effect of the classifier's parameter in the classifier performance. And after that, we go for the hardware and software co-design of the highest performant classifier, aiming at a minimum of 10 frames per second real-time classification performance. In this slide, we show the complete mechatronics classification system, where we have the following blocks. The input to the system is a merged variety. That input will pass through an imaging system, as you see here, an imaging system, and which is by itself connected to the hardware software co-designed classification system for us. And then the output is a sorted variety. The output is a sorted variety, and each container here will have one specific variety. The flow chart of the proposed system is as follows. After the start, we have the image acquisition, and then pre-processing and segmentation, and then feature extraction, and then we do the classification using artificial neural network, SVM, and KNN. The best classifier is to be selected for the prototyping, and then we end up with this. In experimental setup, the image acquisition has the following points: the RGB color camera with these features. We need personal computer, and in lighting to make lighting constant to fluorescent lights. In image dataset, we prepared a database of 600 RGB colored images of a single date. That means 100 images by class. And we used 6 classes. These classes are Khalas, Fard, Khunizi, and Cache, Nagal, and Ma'an. These are the different classes. For the image dataset, as you see here, we have the different types of dates, and as you see from these images, they are different from each other by the shape and the skin, their skin and their color. For processing and segmentation, we have the following steps. First, we resize the image, then we do the color transformation, and then we do the segmentation, and then we do noise removal, and then we do cropping. In terms of real flow chart, we have these steps or the results of every step. We start with the original image. As you see, the image is small compared to the whole size. Then we convert it to a gray level, and then we have to remove everything around the object. At the end, we end up with our original image cropped, and then in gray level we have this one. For color feature extraction, we start by the original color image. We separate the channels. RGB color channel become independent, and then for every channel we do some calculation to extract features. These features are the mean, the minimum, and maximum intensity. Then for 3 channel total we have 9 features in addition to the standard deviation. For shape and size features, we calculate the following features. Then we calculate the area, the perimeter, the solidity, and then the ellipse eccentricity, the major axis length, and minor axis length. The next features are texture features. We use gray level co-occurrence matrix, GLCM, well known. And from GLCM we extract 4 features as follows: the contrast, the correlation, the energy, and the homogeneity. As for classifier, we start by ANN classifier. In general, ANN is noun. We used 3 inputs, 4 hidden layers, and 3 output neurons for the 3 classes or 3 varieties. Then for the network, it should be trained and validated. Training and validation for 30 times. We use different combination of features, different number of hidden neurons from 1 to 10, and then the optimum one. The optimum result in average validation accuracy is used for testing of new. For classification performance characterization, using ANN with these specifications. Transsigmoid hidden and softmax output. Then the features used are the following: texture, we have only 4 texture features, 9 color features, 6 shape size. We use all these features, which are 19 features together. The result is in this star 1. And then using only color and shape, in total 15 features, where the result is the best, as you see here, is the maximum. Then in terms of testing accuracy of different features, when we use only color and shape, we reach 99.2 in terms of testing accuracy using only 7 hidden neurons. As another metric to see the performance of the classifier, we use the confusion matrix. The result is given as the stable, given by the stable. We have 100% of precision, number 1, number 2, and we have only misclassified classified 1 in output class 3, with this one 94.7, and in total we have 99.2%, which is very good. Then compare it to SVM and KNN, ANN is performing much better, and then we continue implementing ANN in hardware. The analysis of the results are the following: the best performance achieved by the ANN with 7 Tansig hidden neurons and the combination of 15 color and shape size features. The accuracy was 97.2%, average recall 99.12%, and the average precision 99.25%. The output classes of the confusion matrix indicate the system's output. Classes 1, 2, 3, 4, 5, 6 represent خلاص, فرد, غنيزي, كاش, نيرال, معان, respectively. Using a combination of color and shape size feature, the highest performance proposed ANN with Tansig network perfectly classifies each class recall of 100%, except class 5, where only one sample is misclassified as class 3 instead of. The embedded system prototyping and performance evaluation. The development platform for this work in this paper, a Zebus Z7 development board is selected. This platform features a Zynq 7020 SoC integrating a dual-core ARM Cortex-A9 processor, 1 GB DDR3, and key peripherals within an RTX 7 FPGA. High throughput communication mechanisms are provided between the programmable logic and the processing system, containing the ARM CPU performing the best of processor and programmable logic in a single chip. Dividing the workload between ARM processor and FPGA is carefully designed. DS-SoC 2018.3 is used to develop a software-hardware co-design for the ANN Tansig. Application profiling on ARM. The original MATLAB code of the ANN Tansig classifier using 15 color and shape features is converted to a C++ program compatible with SDSoC. The results are given in this figure. Feature extraction is the most expensive one. It consumes 54.3% of the program execution time. The preprocessing and segmentation modules consumes 43.2%, and 2.5% overhead is spent in the execution of the remaining functions. In hardware-software co-design, we have the following points. On the basis, profiling result, features, extraction, preprocessing, and segmentation are synthesized as dedicated hardware accelerator. Vivado HLS is used to synthesize these accelerators. Image data are sent in a stream to dedicated raw buffer. HLS stream class in Vivado HLS is used. Each function argument interface of the accelerated modules is specified using SDSoC pragmas to achieve the highest data transfer. Axi DMI is scatter in scatter gather mode is used. Fixed point arithmetic is used for both software and hardware computations. Loops inside the hardware accelerated module are unrolled and pipelined using HLS pragma. The hardware software co-design performance evaluation is given in tables here, where we can see clearly the resources, the FPGA resources utilization for the hardware software in the first table, and the second table is showing the hardware software co-design execution time of each module in reference to ARM CPU software execution. And as you see that the blue one here is for ARM CPU execution time, and the orange is the hardware software co-design execution time. Then from this figure, it's clear that the hardware software co-design is much faster compared to the ARM CPU execution time. Then we can say that pre-processing, the original classification program ARM processor has achieved 0.78 frame per second. The SDSoC integration of features, extraction, preprocessing, and segmentation modules into the FPGA produced 10.9 frame per second. This is representing almost 14 times the speed up acceleration comparatively to the original program implementation. In conclusion, we can say that dedicated embedded computer vision system is proposed, aiming at automatic real-time classification of 6 classes: Khalas, Khriji, Fard, Cache, Nagar, and Mahan, dates, fruit varieties. The system starts with preprocessing and segmentation of the colored image. 15 color and shape size features are extracted and are then fed into an NaN and Tansig classifier. The performance of the proposed system at perfectly classifying each class is experimented, and 97.26% highest classification accuracy are achieved. Hardware software co-design is implemented using a selected Zynq 7020 SoC platform on the basis of the ARM profiling results of the original classification algorithm. Features, extraction, preprocessing, and segmentation modules are synthesized as dedicated hardware accelerators. The proposed hardware software co-design has achieved 10.9 frame per second real-time classification performance. This performance is acceptable and represents almost 14 times the speed up acceleration comparatively to the original program implementation. At the end, thank you very much for your listening, and if there is any question, then we can chat.